Okay, great. So the title is From the Holocene to the Anthropocene to the Noosphere. The question here is about the evolution of planetary intelligence, but since, as we're talking about, we don't really know what planetary intelligence is, what I'm really going to focus on are planetary transitions. And what I've been particularly interested in, like David, is the planetary transition of the Anthropocene and what that sort of means. What does it mean to get through it? So there's going to be some focus on that. Okay, so I'm going to start off with a question. Which one of these is the Earth? Answer? They want to answer? All of them. Yeah, you guys are so smart. Right. So, that's the Earth and the Hadean, when the planet was mostly molten. There have been times, actually this amazed me when I learned it. The Earth was initially a water world. There were no continents. There were just these little cratons, as they called them. Sometimes the Earth has been, the temperature, like during the PETM, the temperature was like 15 degrees higher. So we've been a jungle world with almost no snow or ice on the planet. Sometimes the planet has been entirely covered in ice in the snowball phases. Here's our happy world now. And this is, as the sun heats up, the oceans will be boiled away. So the point here is that the Earth has been many different kinds of planets. There have been dramatic transitions between them. And the idea is thinking about what the transition we're going through now is about. But also, as Sarah talked about, the earlier transitions and life, the way life has been playing, because in many of these, life has been playing a fundamental role in going from one transition to the next. So what we're really interested in is the idea of the coevolution, and we're going to unpack this, of the coupled planetary system. So here, David showed a version of this. This is one, I liked what this artist did with this. All of these different eras and epochs and eons of the evolution of the Earth. And all of these should be thought about as coupled as a bunch of different systems, which are in the planet, that are strongly coupled together. The atmosphere, the hydrosphere, the cryosphere, which is the ice, and the ice plays a very different kind of role than just the hydrosphere, the lithosphere or geosphere, and now what we're really going to be focusing on a lot in this talk is about the idea of the biosphere and its transformations. Okay, so right now we live in the Holocene, right? So that is the epoch that we live in currently. And you can see the evolution. This is going back thousands of years, so back to 450,000 years. This is the temperature change, and you can see the temperature jumping up and down. And each one of these here, when it's poking above, this is the current average over the last couple of centuries. This is these are interglacials, right? And you can see this also in terms of this is the volume of ice, and at every interglacial, the amount of ice drops down. So we are really living in just one of these short periods, which we call the Holocene, that's an interglacial. But what's interesting about the Holocene is that is the entire history of human civilization. And by civilization, I'm referring specifically to what happened once we started agriculture, once we domesticated ourselves, right? So the entire history of human beings and agriculture and city building and technology building and the technology that goes with cities, irrigation, etc., writing, all of it fits into this last period since the ice ages ended. So the Anthropocene, the idea of the Anthropocene, and David has talked about this, is that it is now a human-dominated era. When we think about the coupled planetary systems, we've now moved to a point where human beings are actually the dominant force in pushing those systems around. So obviously, everyone loves this picture because it's just so dramatic. But there's a lot more than just to the Anthropocene than just lighten up the night side, right? So this idea of boundaries in the Anthropocene has become very important because what we fear is that if we cross these boundaries, and those boundaries are about the coupled systems, if we cross these boundaries, then we're going to be pushing the Earth into a new state that's not the Holocene anymore. And we're already starting that, and the question is how far we push it. So I wanted to look at some of these boundaries that have been identified. So this comes from a couple of papers by Rockstrom, Stefan et al. So climate change is clearly one of them, rate of biodiversity loss, the nitrogen cycle, the phosphorus cycle, right? How much of these elements are moved around on the planet? We now are the dominant means of pushing those elements around. It used to be, just non-conscious forces, but it's now our intentional activity which moves that around. Ocean acidification, etc. So I don't want to go into this too much, but the point is, so in this diagram, the further you are getting to this level, that means the closer you've gotten to affect, to pushing to the boundary. So some of these, like genetic diversity, we're already at what people think is the boundary. Now, of course, it's very debatable about what the boundary is, but it's the idea of that there are boundaries that tells you, A, that we're pushing past the Holocene. Those Holocenes were Holocene boundaries in terms of the function of the coupled planetary systems. Now, the point is also that life has done this before, right? This is not the first time that life has pushed on boundaries in the planetary systems. So David talked about this yesterday, but this is the great oxidation event. We're seeing is time in billions of years. The amount of oxygen in the atmosphere was 1 million times less back then. And then somewhere around 2.5 billion years ago or so, through the activity of life, through the evolution of a new process, oxygenic photosynthesis, the oxygen content in the atmosphere exploded, right? And it's because of that, suddenly, that all of these things like big brains were possible. So this utterly and completely transformed the evolution of the planet, the great oxidation event. And so what are we doing now? Well, what is different from what human beings are doing in terms of changing the chemical composition of the atmosphere than what was happening back then? So we see from the great oxidation event, this is the example of life affecting or changing the coupled planetary systems in a ways that has a profound effect. And it's also noteworthy that this didn't work out so well for the creatures that did it, right? They're in places like your gut or in places where there's no oxygen, because these critters couldn't live in any place that had oxygen. Now, this leads us to the Gaia hypothesis that we're going to be focusing on quite a bit. And the Gaia hypothesis proposed by Lovelock and Lynn Margulis was that all living things on Earth function as one superorganism that changes the environment to create conditions that best meet its needs, with the idea of self-regulation. Just like your body will have a temperature of 98.6 degrees, whether you're in the desert or whether you're in the Arctic, the planet has the Gaia hypothesis was the idea that the planet can regulate itself. And here's this great picture I found for the book that I wrote of James Lovelock and Lynn Margulis, and this is in his on his land. That's a statue of Gaia. Now, of course, when Gaia hypothesis was proposed, scientists hated it. Right? There was an enormous pushback from biologists. And it was because, unfortunately, of people like Oberon and Morning Glory Zell Ravenheart, who were literally priests of Gaia, right? Yes, that is a baby unicorn there. So, Gaia got embraced by sort of the New Age movement because, it was very groovy, Mother Earth, don't mess with Mother Earth. And it was that kind of sense, the Earth's a living thing, the Earth has a mind, the Earth wants this or wants that people pushed back on, because really it was the idea of teleology, right? What we know from evolution is, evolution doesn't have a teleology, it doesn't have a goal, it's not trying to go anywhere, it's a, random process of innovation. So this is why people pushed back on it, and what happened eventually was that, the name Gaia got dropped, and what we got was Earth system science, right? Earth system science replaced Gaia. People recognized that the Gaia hypothesis had made a huge contribution, because what was important was it recognized the fundamental role of life in the co-evolution of between life and the planet. And so that stayed, but the idea of the planet wants something, the planet is a living thing, that was sort of dropped. And I think actually it's time to bring that back with a more subtle understanding of it. But coevolution here is this idea that the planet on this side and life on that side are always affecting each other in global transitions, and that's what we're interested in, because we're interested in intelligence as a global transition. But you first get oceans, and then you get the first fossil organisms, but they are methanogen, so they change the climate, and then so that changes the overall state of the planet, and then life evolves oxygenic photosynthesis, that changes things again. So there's been constant, life has always been a fundamental player in the evolution and the evolutionary transitions of the planet as a whole. So now I want to think about how astrobiology informs our discussions of these topics. So what astrobiology does is it looks at the Anthropocene, right, which is something that seems to be very particular to us, to this one planet in this one location in the galaxy. And it says, you know what, this may be a much more generic kind of transformation that occurs when any planet, anywhere, evolves a technological species. Okay, so it's what I call the 10,000 light year view of what we're going through right now. Now, I won't go through in detail what astrobiology is, but I do want you to know that, so astrobiology is basically the study of life in its planetary context. And you might say, like, well, we've only got one, what kind of study is that? But the point is astrobiology is really an amazing field now because of three profound revolutions, the first of which is the discovery of exoplanets orbiting other stars. This is a 3,000-year-old question. We didn't know whether any planets existed other than the ones around the sun until just like 20 years ago. And in fact, at the turn of the last century, there was reason to believe that planets would be incredibly rare. So now we know that every star in the sky has planets, and that if you count up 5 of them, one of them is going to have a planet in the right place for life to form. So that's one important part. The other important part is we've been sending robot emissaries to pretty much every kind of solar system body that exists, right? We've had Mars rovers rolling around for quite a while. We know a lot about planets. Most of all, we know a lot about climate, right? We've been able to study, we have computer models that can predict the weather on Mars tomorrow. Okay, so when people tell you like, oh, those climate models, they suck, they can't tell you anything. It's like, oh yeah, really? Then how do I know the weather on Mars or Titan or Venus, okay? So climate now, we don't know about climate just because of the Earth. We know about climate as a generic planetary phenomenon. And also, we've been able to explore in detail Earth's past. And that becomes a proxy for us. All the different Earths that have been become a proxy for understanding how other planets and their life may evolve, okay? So this leads to a very interesting question, right? Because, we think about the transition we're going through right now with climate change, and we want to develop a sustainable version of human civilization. But the question we should really be interested in, that only astrobiology can ask, is how do we know that even is possible, right? How do we know that there's such a thing like that in the universe, right? So we know that the universe makes comets, and it makes black holes, and whatever else you want to add, interstellar clouds. But we don't know that sustainable, energy-intensive civilizations like our own are part of the cosmic inventory. It may just not may be something that's just not possible, right? That every civilization, if they form, they arise, they flare out after a few hundred years, and then the biosphere just kind of consumes them and moves on. And so that's a question that we can actually look at when we start imagining, we take into account the possibility that there have been other civilizations, other places. Now, right, the specific questions are that you want to do, if you're going to do the astrobiology of the Anthropocene, the specific questions you want to address are, how common are Anthropocenes? How fatal are they, right? And along with this line is David's question, when David was talking about what is the average lifetime for industrial civilizations, or at least what is the lifetime relative to triggering climate change, right? There may be other existential dilemmas out there. Maybe if you're for million-year-long civilization, there's a new kind of existential crisis that we can't even imagine, right? But certainly climate change is you can imagine climate change may be a filter, a great filter for young civilizations. And most of all, for this conference, what are the characteristics of planets with long-term industrial civilizations, right? Is there something that every civilization that manages to get through their Anthropocenes, through their bottleneck, that you just end up with sort of generic kinds of properties for the planet? Okay, and we'll talk about that. And this obviously relates to the transition to planetary intelligence. I will just note, you may say like, yeah, we don't know whether there's any other civilizations. It's true, we don't know if there's any other, but Woody Sullivan and I did a paper a couple years back where we basically showed that unless the odds on, if I just gave you a random planet, right, unless the odds of developing a civilization on that random planet are less than 1 in 10 billion trillion, okay, then it's happened before. Because that's just, and that's an empirical number that comes from just looking at the number of habitable zone planets there are in the universe. So 1 in 10 billion trillion is pretty small, right? That's, so what we're saying is, as long as nature's odds per planet are bigger than that, then it's happened before, okay? So that really sort of points to the idea that statistically, there's been a lot of experiments the universe has gotten to run. And you're gonna tell me that, after a 10 billion trillion experiments, we're the only time it happened? So what it tells you is unless the universe is biased against it, has some real reason, so to speak, in terms of the laws of physics and evolution against it, then we are not the first time that an industrial civilization has arisen. Okay, So in order to do this, though, so we have to take exo-civilizations seriously. To take this kind of astrobiological route in thinking about what's happening to us, we have to take exo-civilizations seriously. And, not for detection, not for biology, and not for sociology, because detection, we could actually do that, but that's not what I'm interested in now. Biology, there's not a whole lot of questions we can answer when it comes to exo-civilizations and their specific biology. Do they have 8 fingers? Do they have, 2 heads? There's just no rules that we can use in terms of the science that we have. And not sociology, because God knows what alien economics looks like, right? The one thing we can do, though, because we know so much about planets from what we've learned from astrobiology, is we can focus on the coevolution of civilizations and their coupled planetary systems. We actually have laws there that we can apply to this problem. Okay, so means we have to get past thinking about aliens and kind of giggling about it. Now, of course, the reason we do that, we giggle, is because of prosthetic foreheads, right? We've had decades of, bad science fiction, TV science fiction, where the aliens always have little antennas or something. But it's time to get past that, because astrobiology has gotten past that in terms of showing us all the planets there are out there and, all the possibilities. And so it's time to take exo-civilization seriously, because in some sense we're one, right? We're just a particular civilization, and I can argue that odds are overwhelmingly that there have been others. So now what we want to do, if we want to do the astrobiology of the Anthropocene, is calculate the trajectories of exo-civilization planetary evolution. Now, how can I do that? How can I use the laws of physics and maybe some simplest biology possible to do this? Well, one way is using what's called dynamical systems theory. This comes from some papers that my group wrote. And dynamical systems theory, the most familiar example, if you don't know about it, is predator-prey models, right? You got some wolves, and you got some cute bunnies, and the wolves going to eat the bunnies, and you can actually write down equations for that interaction between these two species. It's called population biology, and what you find is there are these amazing cycles that occur. The bunny population rises very quickly, and then the wolves start eating them, and then they eat so many that the bunny population comes down, and then the wolf population comes down. So we can use the very basics of population biology to try and do some models, and I'm not going to, there won't be a test on this, but this was the beginning of our dynamical systems equations. We had an equation for the population of a technological species, and we had an equation for the state of the planet. Think of the planet's temperature, and they're coupled. The more the more the aliens used the energy resources of the planet, the more alien babies they made, and the more alien babies there were, the more the more they used the planet's resources, which changed the planet. And the interesting thing about this took me a while to figure out how to do this, because I don't do population biology. So in looking through the literature, I actually found the version of the equations I wanted from models of Easter Island. Right? And so Easter Island is the example of, of ecocide, right? Of, eco-catastrophe. So this is this, version, this came from the press release for the paper, and a version of Easter Island for aliens. But it's interesting that that's where I actually found a version of the models that I needed. So actually the models got more complicated because we wanted to put in some measure of the ability to switch resources. So you're a population, you're using some energy resource, it feeds back on the planet's temperature increases, but we wanted to include the possibility that, you may recognize something's going on and you're going to switch to a lower impact resource. So that was just in those equations. So let me show you what comes out. All right, so there were some broad classes of behavior that came out of that, and they are all transitions. They're all about planetary transitions. So, in these models, green is the population, the population of the planet, and red is the planetary temperature. Now, you can think of it that way. So first we found 3 classes of trajectory. The first is this one. We called it die-off, right? So the population in green starts using the planet's resources, skyrockets, right? You get this very rapid increase in population. The planet heats up. As the planet heats up, it makes it harder to have alien babies, or it actually increases the death rate. So imagine, just like we saw this summer, more fires, more hurricanes, more heat waves. And then the population, there's this big die-off, but then everybody comes to equilibrium. You stabilize out here. So the model has found an equilibrium. So, that's you know, it's not clear. Depending on how big we found die-offs as much as 80% of the population. It's not clear that a technological civilization, which is very stratified and it's a bunch of coupled networks, whether that would survive. But at least you came to a stable equilibrium in the end. We also found sustainability. We called this the smooth landing, right? The population goes up, the planet heats up, but you come to a nice equilibrium without any kind of dramatic tragedy. It's funny when, you know, this got a lot of press and everybody's like, you know, aliens die from climate change, and nobody focused on this. And I had to keep, you know, like telling people, look, there are sustainable solutions in these toy models. That's a big deal. It shows you that, at least as far as these models go, there are long-term sustainable versions of civilization. And then, of course, the most dramatic and scary ones are these die-offs, right? Where the population rises, the planet heats up, and then the planet just kind of goes into a runaway, and then the population comes down like a stone. Even more scary were these solutions where you switched from the high impact to the low impact resource. And you can see that right there, right? The planet's heating up, you're using fossil fuels, and then you're like, no, we gotta go to solar power. And so you switch to solar power, and for a while, everything looks groovy, and you're like, yay, we saved the planet. And then it doesn't matter, you know, the planet still switches into a runaway, and then the population drops to collapse. And the reason that happens is because coupled planetary systems are non-linear. In other words, they have a mind of their own. You start pushing that rock down the hill, you know, by driving the planet into a new kind of climate state, and you can't say for sure what the consequences are going to be. And once the planet starts rolling down the hill, it's got its own inertia, so to speak. And, you know, this is from a dynamical systems perspective. It's, you know, you're rolling into a new attractor basin, as they would say. And, you know, so that was very sobering. That even if, now these models are, I want to emphasize, these are very simplified models. And the next step that we're going to do is to build in actual climate models for the response of the planet. Okay, now what we want to do with these is to actually do a theoretical calculation of that, what is the final factor in Drake's equation that David talked about, L, right? Because, you know, you raise an interesting point about the immortal civilizations, but let's say there is an average, a meaningful average, then we want to know what that meaningful average is. And from these models, as we get more sophisticated, we ought to be able to tell this transition, you know, what fraction of these civilizations, and on average, make it to a long-term sustainable state, right? So this is an important number for us, because if in general what we find is technological civilizations have a 200-year lifetime before they collapse under the Anthropocene transition, then we're in trouble, right? It means that almost nobody makes it through. If that number is 2 million years, then in some sense what that means is you have a lot of wiggle room. There's a lot of ways to make mistakes and still recover in your choices, right? So we talk about planetary intelligence. We're going to have to make choices. Those choices are going to involve that is in planetary intelligence, in some sense, collective choice. And the question is, are we making the right collective choice? Okay, so now let me switch over to ask a different question, which is very relevant to what we're doing today, which is what does the outcome of making the right choice look like? I want to ask the question about these transitions a planet makes, and eventually, what does it look like if you make it to a long-term sustainable version? So what are the characteristics of that? And so what we did, this was a project we worked on last year, we proposed a classification for system for planets based on how much free energy generation occurs within the coupled system. This is a thermodynamic concept, which I won't unpack right now. We can talk about it later. But it's basically how the ability of the planet to take sunlight and then do interesting things with it from a thermodynamic perspective. What kind of new innovations can it make? So again, not about detection, but it was all about the thermodynamic interactions between the coupled planetary system and an exo-civilization, okay? And again, we mentioned this at the workshop. This scale that we're proposing for planets is very different from what's called the Kardashev scale. I won't go into this great detail. Some of you may know about it. But it was the idea that planets progress up, or civilizations progress up this ladder of different types based on their energy use. And in type 1, the civilization used all the energy that was available from the sunlight that was falling on the planet. And my idea was that that's a kind of planetary brutalism. The whole lesson of the Anthropocene is it's not just about energy. You can harvest all the energy you want, and you may still push your planet into a different kind of climate state. You have to learn to think like a planet, right? You're going to have to somehow integrate yourself back into the biosphere so that you're not pushing it into states that you can't handle. Okay. All right. So yeah, you can't bring planets to heal, but maybe you can bring them a plan, right? And that's the intelligence part, right? So I won't go into this in great detail, but really what we were interested in was energy, entropy, and the cascade of processes as you go from driving climate. So for example, the sunlight falls on the planet and it warms the air, and then you get air rising, and you get evaporation, and then as the air rises, some of those material, the volatiles, condense out into rain. And so that's a very fundamental process. There's power in that process, and it's climate power. And then what happens is, by moving stuff around, that climate power ends up triggering chemistry on the planet. So climate power turns into chemistry power, right? And now if you've got biology around, that chemistry is going to be harvested by the biology, and the biology is now going to have power. You're going to make sugars in your cells, right? So climate power turns into chemistry power, turns into biology power, and if you have a technological civilization, that technological civilization is harvesting the biology power, at least in the beginning, right? You're going to be eating other stuff, right? The bread you ate this morning is technology harvesting. Is the harvesting of the biopower to make technology power if you went out and built a computer or something. Okay, so this diagram just shows the basic idea of that you have sunlight coming in and radiated, heat radiation coming out, but you also have low entropy. This radiation has low entropy. This radiation has high entropy. And in between it, you have all of these transformations that are driven by this flux of radiation and entropy in, and a flux of radiation and entropy out. And it's this cascade from, climate power to chemistry power to life power to the possibility of technological power that really is the driving force for the transitions, right? Because what we're interested in are the transitions that can occur in a planetary evolution. So as Sarah was talking about, somewhere in between here and there, right, was the evolution of life, right? The planetary transition that makes life. And so let me show you, another schematic for this that might be useful. Okay, so what we proposed was that that in these transitions, there were going to be 5 classes of planets, and those classes were relevant to the kinds of processes that were available. So a class 1 planet was like Mercury. All you have is radiation falling on the planet. There's no volatiles. There's no fluids. So all you can do is heat up the surface, and it'll radiate back into space. In a class 2 planet, you had an atmosphere, and that atmosphere, once you warmed things, once you warmed the ground from sunlight, now you got rising air currents and the possibility of rain, and then you get chemical cycling as the rain rolled off the rocks and eroded the rocks. So there was a bunch of different kind of power made available, power for doing things and for evolution that was available here that wasn't available there. Now once you get life, even what we called a thin biosphere, and we were talking yesterday about whether that's a good term, but the idea that in what's called the Archean, the first era of life on the planet, that life still wasn't really strongly coupled, right? It was changing some of these processes by doing some it allowed new kinds of chemical cycling to occur basically into that system. So it was changing these systems. That's what the green arrow here shows. And into the ocean you see the green dots. Things are changing on the planet now in terms of these cycles. But it's not that life isn't dominating. Then you get to a class 4 planet, which was like Earth, say 10 million 10 million years ago. A thick biosphere where you see all the green arrows. All the processes now are being altered by the planet. Just the roots and leaves, the fact that they're all over the place on the Earth, fundamentally change how evaporation occurs. Right? That's an example of this. So here you see every process being mediated by the presence of life. So geologic decay cycling, atmospheric, biospheric cycling, that's what all those arrows are. And what we proposed was that once you get a long-term, sustainable, technological civilization, that it becomes a new player in this. And so now the orange here is showing you can see there's little wind farms here, solar panels. Now it's the technological civilization, in order to become sustainable, to become long-term, had to figure out how to come into some kind of cooperative relationship with the biosphere, such that it is now also a player, but a long-term player in these biogeochemical cycles, right? So now they're biogeochemical technological cycles, okay? Thank you. So that's the idea of a class 5 civilization. And so this was just, a model, some images of their, planet with no life, class 1, class 2, class 3, class 4, and by class 5, you can kind of see the hints of the technological civilization. So how much time do I have left? 5 minutes, okay, good. All right, so I won't go into that. We can come back to this, but you can actually see, we believe you can see traces, you can observe traces in terms of chemical disequilibrium in the atmospheres of planets in all these different stages. Okay, so to sum up, what the astrobiology of the Anthropocene does is it allows you to tell the right story about what's happening to us. The wrong story, as Dave was saying, we're a plague on the planet which must be saved from us. The right story is we are what the biosphere is doing now, right? Which doesn't mean we're going to be what the biosphere is doing in 1,000 years, and the Earth will be happy to move on without us, right? But we are a transition that the planet is going through. We are the latest round of biospheric innovation. The question is it long-term or is it just a short-term flash in the pan? And also that comes out of this, I do a lot of work with the public and I'm always being asked, did we change the climate, right? And that's the wrong question. The right question is, of course we changed the climate. We built a world-girdling civilization. What else did you expect? So now let's end up with, I'll go past that. What do we expect to happen next, right? And so this comes to the idea of planetary the planetary intelligence, right? So I want to introduce the idea of the noosphere a little bit more. So it is it was actually developed first by Vladimir Verdansky, who is the guy who came up with the biosphere. He was a Russian biogeochemist, but only because he invented those fields. There was no geochemistry, there was no biochemistry or biophysics, or, he's the one who sort of thought you got to think, he was the one who invented the idea of the biosphere. It was his term. So he was interested in the idea, after coming up with the biosphere, he started thinking of human thought as an analogy to the atmosphere or the biosphere. And there's this great line where he's just on the night before he proposes it, the noosphere. He comes up with, I've been working on the lecture. For the first time, I will say something concerning my thoughts on the intellect of man as a force on the earth. So he then proposes, in that lecture, and then he proposes this idea that at some point thought becomes its own sphere. Just like there's an atmosphere and a biosphere, you're going to develop a sphere of thought that becomes dynamic and changes the Earth. So let's just read this. Intellect as a form of biogeochemical energy is proper not only to Homo species, but to all living organisms. That's going to be important for us. However, among these, this energy appears insignificant compared with ordinary biogeochemical energy and is barely noticeable in the balance of nature, and then only on the scale of geologic times. It is associated with the mental activity of organisms, with the development of the brain in higher forms in life, and only with the appearance of reason do its effect produce the transition of the biosphere into the noosphere. The no means intellect, right? So he's saying that, yeah, there's been cognition and intellect, but it hasn't really risen to the point of being a force of nature, and with us, it becomes one. There's also de Chardin's version of this, he was a Jesuit priest and paleontologist, and he was the one who came up with the name noosphere. And he said, because he came from a religious point of view as well as scientific, he said it will be the end and fulfillment of the spirit of the earth. So he sort of had this idea of a world soul. Okay. Now, de Chardin's version of the noosphere is the one that became more well known, but I'm a little bit more, I can feel more Verdansky's, because that version of the noosphere, of a sphere of intellect, is a little bit woo for me. However, on the way to that Gaia festival, that we were all heading towards, we ended up building a noosphere, right? The internet is a version of the noosphere, right? The world is now literally enshrouded in thought. I hold my hand up, and right now, there's waves of thought passing through my hand in the wireless that's running through this room, right? All your Google searches, are passing through my body right now. So, as perhaps freaky deaky as the noosphere might seem, we just ended up building one, without really knowing it. And so the real question asking now is what role can the noosphere, or what can the internet as a beginning of a global mind, what role can it play in acting as a control, right, on the problems we're facing heading into the Anthropocene. So this may be the most important transition. This and the Anthropocene together may be the most important markers of this next planetary transition that we're headed in. But as we talked about, as we've seen what's happened with elections over the last couple of years, is that it almost seems like the internet, the global mind has gone insane. Or it's immoral, I think, which we'll talk about later on. So that's an interesting thing. We think like, oh, it's great, we have a global mind, but maybe. Okay, so I'll come to my end now. Basically what I think is what's happening is humanities at the end of its childhood. Famous science fiction story, childhood end. So the idea is that planets have these rules. We have to learn how to think like a planet, right? Planets have already they've already gone through transitions. We're just another one of them. We have to understand how to put ourselves back into the biosphere. And sustainability, what it means really is an awakened planet. It's a planet that is, to become a sustainable version to develop a sustainable version of civilization. You have to come up with, the planet has to become awake to itself so that both the biosphere and the civilization can flourish in entirely new ways. And so, so this is what's really interesting to me. We talked about Gaia and that pushback with teleology. Well, guess what? Once you have a civilization, you've completed Gaia. Yeah, now you do have teleology because that's what a civilization is about. So maybe the Gaia idea was right, and it just required, the final state for it is the evolution of intelligence. Okay, so I'll just end there. These are the papers, and that's also the book I wrote on it. So thank you very much. I appreciate your time.
So we do have time for a few questions.
No.
So just quickly, and at the end note, are you familiar with Harold Bloom's The Global Brain, the book?
I'm aware of it, but I've never read it.
Because it's kind of an extension of Verdansky and Chardin, and then bringing it, and he talks about the internet.
Right. Okay, so that's something I will definitely look at.
Yeah, and he talks about systems theory and such, and I think it's an updated version of some of this stuff.
Okay, yeah, because I think, and that's kind of what we're here to talk about, right, is sort of what this, oh my God, I don't want to look. All right, no action is needed. Oh yeah, some action's needed, pal.
Is that what it says? No action?
That's what it says.
Oh, God.
Presidential alert, no action needed.
Oh my God. Okay, do we have another real question or real thought? Okay.
As opposed to my thing, right? Not yours.
No, when you speak of the internet, the next phase that the communications industry is going to is 5G. That's gonna be like a turbo boost.
Right.
So, do you have any thoughts on that? What's the extension of your thinking going forward when somebody talks of 5G to you?
Well, it's not 5G, so let me go. But the specifics of that I don't know. But what I'd say is chips into brain, right? I mean, at some point, right, you can imagine the extension, and this is certainly something science fiction writers have talked about. That you're not going to be holding a device in your hand, So some kind of wetware, brain to computer interface that you'll be carrying it with us all the time. That's something I see really being possible. And that's going to be interesting, the degree to which we are sort of always now connected to that system and what that means for how society, because again, I'm really struck by this idea that we built the beginnings of this global mind, and almost very quickly it led us down a dark path, or at least parts of it are. It's obviously amazing things that are happening, but it also, especially at least for democracy, started to undermine or erode sort of the functions of it. So, I don't know.
You're assessing that based on your value system, though.
No, that's true. That's absolutely. Look, I know that's absolutely true.
Okay, so we're out of time for questions on Adam's talk. Thank you so much. That was really thought provoking and great. So thank you again. Thank you.